All right, Assalamu alaikum. So today we're going to look at the mechanism of conduction of impulses, electricity inside the human body. So specifically, we're going to look at nerve action potentials. All right, so what have we done in this course so far? We've looked at the cardiac system and we've tried to describe the cardiac system by through pressure and flow. We also looked at the cardiac cycle and correlated pressure variations with what's happening in the cardiac cycle. But we still don't know, why does the heart pump? How does the heart pump? The trigger is of an electrical origin, and we left it at there. And then we entered into the second module of this course, which we aptly labeled the spark of life. And in this module, we started looking at the origin of electricity in the human body. So in the previous lecture, I just gave you an overview of capacitance, charges, electric fields, potentials, potential energies, and how current flows, right? So I tried to compress all of electric circuits in a single 45-minute lecture. All right, so now we're going to take some of these concepts and see how electrical impulses are transported inside the human body. And this is the very essence of life. Today, we're going to look at the problem from a qualitative perspective. First, we're going to look at the phenomenon. Okay, so what happens? In the next lecture, we're going to look at the phenomenon from a quantitative perspective. We're going to come up with an equation that describes the flow of electricity in the human body. All right, so today is phenomenological. Which means this is how the current state of biological research is. How does an impulse travel on in the human body? Specifically, we're going to look at neurons. Okay, so nerve action potential. A nerve is a bundle of neurons. We know that nerves transmit signals from some sensory organs to the central nervous system, and then from the central nervous system to the motor organs or the effectors like muscles. All right. So all of this, however, has a deep physical basis. And the answer lies in simple physics. Simple physics comes to the rescue and describes how these extremely complex phenomena take place and give life the meaning that we know it has today. So first of all, I would like to start by just reminding you of the process of diffusion. So if I have a membrane, okay, life has its affinity with membranes. What's happening across a membrane is determining our fate as an organism, as a civilization. So this is the membrane, could be perhaps the membrane of a cell. So if I have some molecules on one side of the membrane, and suppose this is a liquid, and there's some concentration of molecules on one side, and there is, so let's call this C1, and there is some concentration on the other side, C2, okay, some molarity or some concentration, and there's a concentration gradient. So there is some delta C, C1 minus C2. Now what this concentration gradient is going to do is that if this membrane is selectively permeable to these molecules, so it has pores which are big enough that these molecules can pass through, then this concentration gradient is going to cause flow of or diffusion of these molecules across the membrane. There could be some molecules moving the other way around across the concentration gradient as well. But on the whole, there will be a higher diffusion from left to right than from right to left. And this process is going to stop, but the concentration is equalized on both ends. So this is the phenomenon of concentration gradient. The flow of ions due to diffusion, of molecules due to diffusion, has to be proportional to the concentration gradient as well. Okay, so this is something that we already know. All right, now what we would like to do is, so what is driving this process? Do we require some external energy so that this process can take place? No, it's a passive process, which means that if the temperature is above 0 kelvins, so you're not at absolute zero, but at some temperature, and organisms are generally at room temperature, at the body temperature, okay, then this process is going to happen all by itself because these molecules are in random motion, which is called Brownian motion. So even if they weren't, even if this were an impermeable membrane, these molecules would have been jostling here and there, okay? So if I focus my attention on a single molecule, it's going to do this random walk. And this energy, the amount of this energy is generally given by kBt, where kb is the Boltzmann constant. This is a magnitude of the thermal energy that is available to the system. Okay, this appears as the internal energy of the system. You increase the temperature, this motion goes up. All right. Now, suppose this is a cell membrane, and we focus our attention on one kind of cell, which is called a neuron. Okay, let me draw a neuron. There are many kinds of neurons, but let me attempt to draw one kind. All right, so this is the structure of a typical neuron. This region is called the cell body or the soma. And there's a long filament that extends from the soma that is called the, what is it called? The axon. Okay, generally one finds the cell, the nucleus inside the soma. All right, and just on the periphery of the cell body, you will find these tentacles extending, and these are called the dendrites. All right, so the neuron picks up signals from neighboring neurons through the dendrites, and the message through a nerve impulse is transmitted across the axon, and it reaches the end of the axon where it starts talking to another neuron. And the two neurons do not make physical contact. There's a gap between neurons, which is called a synapse. So there is some chemical communication that happens across neurons over the synaptic gap. So this is the general structure of a neuron, and neurons come in two variants. One is the kind that we see here, and in the other kind, the axon can be covered by an insulator. Okay, an electrical insulator. Now this is slightly ironic that you would like to conduct electric current, but then you have an insulator on the axon. Nevertheless, this is a covering made up of cells, and this covering is called the myelin sheath. And there are gaps between these myelin, these coverings, and these gaps are called the nodes of Ranvier. So this region is exposed. It's not covered by an insulator. So this is the cell, and there is some fluid inside the cell. So it has an intracellular environment, and there is some fluid outside the extracellular environment. All right, so this is the general structure of a very simplistic representation of a neuron, one of the kinds of neurons. An electrical impulse has to travel on this structure. Now we started off our discussion with diffusion. Now I would like to make one like to take a section from the axon. So I just cut this axon and draw it here. And I consider this to be a cylinder. This is the axonic fluid inside the intracellular region. This is the extracellular region. All right. Before I am able to do that, let me draw the semi-permeable membrane again. And instead of molecules, which are uncharged particles, let me consider that there is some ionic liquid, some polar molecule here, and some polar molecule here. Could be potassium chloride, sodium chloride. And if it's in the liquid form, it is dissociated as ions, cations and anions, positively and negatively charged ions. So suppose I have positively charged ions on one side. And for simplicity, I assume that there's nothing over here. There are no ions over here. So there is some solution here, which on the whole is neutral because it's a polar molecule, which in its ionic form, the ions have been dissociated. So there are going to be some negatively charged ions as well. And I'm not going to draw them. Okay, but this region is neutral, electrically neutral. And so is this region. And once again, I have a selectively permeable membrane. Now, by the laws of diffusion that we've just seen, these ions are going to diffuse across the membrane. Let me draw more of these. Okay, and I started off with some small concentration of these ions on the other side. Now, if at time t equals 0, I start the system, these ions are going to diffuse across the membrane because of the concentration gradient. Now, on a whole, this region is neutral. But once it loses positively charged ions, what's going to happen? It's going to pick up a negative charge. And what's going to happen on the other side of? It's going to pick up a positive charge. Now, when that happens, across this barrier, this is the membrane, this region is going to pick up a positive charge, whereas the region here is going to pick up a negative charge. Just because of ionic diffusion. Now, this separation of charges creates what is called a polarization, or an electric field is set up across the membrane. Right? So what's the direction of that electric field? From positive to negative. This is acting like a capacitor now. Two charges are separate. What is a capacitor? Two plates which have opposite and equal charges. So across this junction, which is the membrane, an electric field is set up. And the direction of that electric field, I'm going to show in yellow. Now, what is the impact of this electric field? Let me just finish. Is it going to let diffusion go on unimpeded? It's going to arrest the flow of ions at some stage. Because now these positive charges have to go across an electric field. They have to go uphill. In other words, the potential on this side has gone up. If a positive charge were placed here, it would have a higher potential energy as compared to the left of the membrane. So at some point, the electric field, you can imagine that this electric field is going to impose a force on the positive charges, QE. And the direction of that force is from right to left. So it's going to impede further flow of positively charged ions. And even though a concentration gradient, such a concentration gradient still exists, diffusion will not be sufficient to allow equilibration of the charges or equalization of the charges. An equilibrium will be achieved in which this concentration will drop, this concentration will go up, but eventually the concentrations will not be equalized. Got it? Now we're going to look at this mathematically. Ji, aapka sawal. Right. Right. So let me draw what's happening over here. So if I draw an axis here, I call this the x-axis. Okay. This point I call x equals 0. So this is the positive x, this is the negative x. Now what I would like to do is the following. So here is my axis, x. And here I plot the potential versus x. Now to the right of the membrane, the potential is going up. And to the left of the membrane, it's going down. So this is what my potential looks like. Okay. And then it equalizes. It becomes constant. So this is a region across the membrane which does not have any charge whatsoever. Right? So this is a region devoid of charge. Across the membrane, the charges annihilate, and all the fixed charges are studied over here. Okay. So this is how the potential varies across the membrane. And if you remember, I described in the previous lecture that the electric field is given by the gradient of the potential. Now this is the potential, and this produces a gradient which is a constant. So the gradient of a sloping function is a constant. Remember, this is a linear function, Vx. If I would like to write an equation for this, what would that equation be? Suppose this potential here is V naught. So this is going to be V naught plus some gradient, which happens to be the electric field, X. Okay, so the equation of this part of the potential curve is this thing. You differentiate this dV by dx, you will get E, the electric field in a particular direction. And the direction of the electric field is from positive to negative. This is, so the potential is going up from left to right. This sign shows that the electric field is going from right to left. So when this situation is set up, an equilibrium is established between the concentration of ions. Now what we would like to do is, let me redraw this figure over here so that I don't have to shift blackboards. So this is my membrane, a positive charge over here, a negative charge over here, all right? And some ions over here, some ions over here. Suppose this concentration is C1 and this concentration is C2 after equilibrium has been established. Now we would like to use some basic principles of physics to find out what the ratio of these concentrations is once equilibrium has been established. All right. Now, how are we going to do that? Can you come up with some idea of how we can find the ratio of these concentrations? Just I give you 1 or 2 minutes to think about it. Some physical principle. It has to do with potential energy. Exactly. So the ratio of these concentrations has to depend upon the potential energy of an ion in this region versus the potential energy of an ion in this region. In other words, the ratio of the concentrations has to depend upon the difference in potential energy between the left and the right. It has to depend, therefore, on the potential difference between left and right. So we have to relate this ratio of concentrations to potential difference, to voltage. Remember that if I were to take a voltmeter and put the two terminals of the voltmeter across this membrane, the cell membrane or the neuronal membrane, and if there's a concentration gradient and these ions are charged, I will pick up a voltage, some voltage, perhaps in microvolts or millivolts, but some voltage is going to exist. Now, आपका नाम? Ibrahim has provided a very lucid answer and he's helped us think in the direction of energy. So higher the energy, lower will be the concentration there. Lower the energy, we expect the concentration to be higher. So if I give you the example of the atmosphere, suppose I take a column of air, and this is my sea level. And I have some gas, say nitrogen. So as we go above the sea level, the concentration of gas, which is proportional to the pressure of the gas, is going to drop. So if I'm at a level H above sea level, what is the energy of a molecule over here? What's the energy of the molecule, the potential energy of the molecule at a height H above ground? mgh. U equals mgh. Let's call it X for correspondence, mgx. All right. Now there's a physical principle which is called the Boltzmann distribution, which applies to systems, to most biological systems, which helps us relate the number of particles at a particular energy versus the energy. So this, for example, would help us determine how many particles exist here, how many particles exist here, or to be precise, what's the fraction of particles that exist at different heights. Okay, so the Boltzmann distribution has a very simple mathematical form. And that mathematical form is that the concentration of molecules in this pressure system at a height x above ground is proportional to exponent minus the energy of the particle at height x divided by the thermal energy kBT divided by some constant n, which is the total number of particles, right? So this is the fraction of molecules in the pressure system at a height x above ground, right? So what you would like to do, you would like to take the energy divided by kBT, which is the thermal energy, as I've described, put a minus sign with it and exponentiate it, and divide by some normalization constant, generally called the partition function. When you study thermodynamics, you call this the partition function, but forget about that. All right. So this is the, so if you take a molecule and want to find out the probability that it exists at height x, this is the formula that you would like to use. And this is called the Boltzmann distribution. So that's why if in this air system, if I would like to plot versus x, so this is my sea level here, and this is my concentration of nitrogen molecules in the column of air, I will have some concentration at the sea level, some concentration. And on top of that, I'm going to have an exponentially decaying curve. So the pressure exponentially decreases as we go above from the sea level. And it's described by the Boltzmann distribution. Okay, in most biological systems, you have an analogous situation. Now we would like to apply this formalism to the transport of ions across the membrane. So here we're looking at ionic transport across a membrane. Right. So therefore, what I would like you to do now is if I were to take the ratio of C1, so could you, so this is what I need to determine. Okay, can I use this formalism to determine what the ratio of these concentrations is going to look like? Give it a shot. I gave you 2 minutes to think about this. Remember that in an electrical system, the energy at some position x is going to be given by the charge multiplied by the potential at x, right? So just take the potential at x. Don't write this in terms of electric field. Suppose the potential on the left is V1, the potential on the right is V2. Okay. And what is the charge on an ion? It's related to the valency of the ion, right? किसी ने किया ये? You just need to put this energy expression in here, right? So what we assume is that our concentration here at the edge is C1. Here the concentration is C2. The potential here, say, is V2. This is V2. The potential here is V1. Okay, now use this figure here to determine what the concentration C1 versus the concentration C2 is going to be. किसी से हुआ जी let's say v1 v2 और v1 कह दिया ना मैंने. Let's say v2. तो c2 में नेगेटिव होगा, c1 में पॉजिटिव होगा. v1 need not be the same as v2. Right? Take it to be arbitrary, v2 and v1. So c1 is going to be equal to exponent minus the potential energy here minus q v1 over kBT divided by some n, right? Now C2, so this is my C1. My C2 is going to be exponent minus q v2 over kBT divided by the same constant, right? Now I take the ratio of these numbers. C1 over C2 is exponent minus V1 minus V2 over kBT. Sorry, with the Q as well. Now, what is V1 minus V2? That's the potential difference. So E raised to power minus the potential difference multiplied by Q over kBT. All right. So by looking at the potential difference, which is measurable, you can find out the equilibrium concentrations of two ions across the membrane. Now, these ions could be potassium ions, calcium ions, sodium ions, chloride ions across the cell membrane as well. The same physics applies to a cell membrane. There's nothing special about a cell membrane from a physics perspective. The same physics models a cell membrane as any other membrane. Okay, so whenever we have ions transporting across a membrane, a potential difference is set up. And that potential difference ensures an equilibrium concentration of ions on the two sides. If this ratio is 1, so you have equal concentration on ions on across the membrane, this potential difference has to go to 0. Now, if I would just try to massage this equation a little bit, take the log of both sides, I will get minus Q delta V over kBT is natural log C1 over C2. All right. So I can, this means that delta V is minus kBT over Q natural log C1 over C2. Now, Q is the charge on an ion. That charge on an ion is simply the charge on an electron multiplied by the valency, right? So I can write this as minus kBT E Z C1 over C2. And I also know that the Boltzmann constant Kb is equal to the molar gas constant divided by the number of ions in a mole, which is called the Avogadro number. Basic thermodynamics. Okay, so I can insert this in here. So I get rid of the kbt. I'll get minus kb r z na charge on electron natural log c1 over c2. Sorry. Sorry. Now what I could do is simplify this a bit further. Delta V, the potential difference across the membrane, R, T, Z, the valence of the ion, 1 for potassium, sodium, calcium. For calcium, it's 2. And what is this number NaE? The charge on the charge and the Avogadro number of ions. So that's the charge per unit mole. Okay. And generally, this is called the Faraday constant, F. So this has units of coulombs per mole. So Na, the Avogadro number multiplied by the charge on a single moiety, equals the charge per mole of the ions. And it's given a name, the Faraday, the constant. All right, so natural log of C1 over C2. And I could, there's a minus sign here as well. I could get rid of the minus sign by inverting this ratio. I could make it C2 over C1. So I get rid of the minus sign. And I would like to change this natural log into log to the base 10. And if I would like to do that, I would like to multiply this by 2.303. All right, so all of these are constants over here. And it turns out to be, so this, what are the units of delta V? Volts. So I have a potential difference across a membrane in volts. If I multiply this with 1,000, I would get the potential difference in millivolts. And if I just solve all of these constants, I know what the molar gas constant is, 8.314 joule per Kelvin per mole. Let's take 37 degrees centigrade, the body temperature as the temperature of interest. F is 96,500 coulombs per mole. I put in all of these values. I can just get rid of this constant, and this would be something of the order of 60 divided by Z log to the base 10 C2 or C1 millivolts. Yes, please. Well, biologists don't understand natural log, so so there's no special reason, right? So this potential is called the Nernst potential. Nernst potential. All right. So whenever you have ionic transport across a membrane, in the transitory phases, the ions move because of a concentration gradient. That is a natural process. A passive process does not require external energy. But once a potential difference is set up, and the potential difference is strong enough that it creates an electric field that impedes further diffusion, the process stops there. And a state of dynamic equilibrium is achieved. And in that case, a potential difference is set up across the membrane. That potential difference is called the Nernst potential, right? So if you pick up a neuronal cell and there's a concentration gradient of ions across the cell membrane of the axon, and you have some mechanism of putting two electrodes of a voltmeter inside and outside the cell, you'll pick up a voltage, some voltage. And that voltage will tell you about the concentration gradient or the ratio of concentrations. Now this C2, so let me recast this equation and let's talk about the neuron in a bit more detail here. And I'll just take 5 more minutes and then we can stop. Any questions? Now this G. So if everything is in a state of equilibrium and there is no excitation, no stimulation of the neuron, this will be the resting potential. And I'm going to explain that. So in a state of equilibrium, when the nerve hasn't been excited or stimulated, this will be the potential across the membrane. Now let's focus on the neuron and the axon in particular. So here I draw a longitudinal section of the axon. Here is the cell membrane. Suppose I have potassium ions, K plus. All right. And this is my, let's say that C1 is my concentration inside, okay? And C2 is my concentration outside. So I'm focusing on the concentration of potassium ions. Generally, you write this in square brackets, millimolars, for example. So my C1 is concentration of potassium ions inside the cell, C2 is outside. Okay, so for convenience, let's call this CI, C out. Okay. Now delta V is V inside minus V outside, right? So this is, so I'm defining the potential difference inside with respect to outside. So my outside is at 0 volts. My reference is outside because I'm taking inside minus outside. Okay. Now if my, so for potassium ions, C inside is larger than C outside. Okay. So when this happens, C1 here is larger than C2. Right? C1, C inside is larger. So this number is smaller than 1. And when I have a number smaller than 1, I take the log of it. Is the log positive or negative? Log of, what is log of 1? 0. What is log of, say, 0.5? It's going to be negative. It's going to be minus 0.693, by the way. Anyway, so log of a number less than 1 is going to be negative. So this number turns out to be negative. The potential turns out to be negative. And what does this mean? This means that this is negative, which means that the inside is at a negative potential with respect to the outside. Okay, so if you look at this axon and just consider the potassium ions, and this is what happens naturally in a state of rest, the inner side of the cell membrane acquires a negative charge. It becomes negatively polarized, and outside the membrane, there is a positive charge. Because the concentration of potassium ions inside is higher than outside. For sodium ions, the converse is true. So for sodium ions, the outside gets a negative charge and the inside gets a positive charge. But in the mix, there are sodium ions, potassium ions, all of them are in the same mix, right? So you have to sum up all of these potential difference. And summing up is not sufficient because these membranes have different permeabilities for potassium, sodium, calcium, and some other phenomenological equation is required to find out the total potential. Now, I would like to stop this lecture by reproducing a table, which is very instructive. So, three ions are of the most importance when considering action potentials. And I'm going to describe in the next lecture what is an action potential. Potassium, sodium, and calcium. So inside, outside, and potential, delta V, inside minus outside. So potassium inside is higher than outside. Sodium, the reverse is true. All right. So if I insert these values into my equation for the Nernst potential, I can find out what the potential is. This is negative, as I've just described. And this turns out to be minus 75 millivolts. This is plus 55 millivolts. And here I have minus 67 millivolts. All right. If I just had potassium ions in my cell, the sodium ions were depleted, a state of disease, or the calcium ions were depleted, this would be my potential. Inside will be negatively charged, outside will be positively charged, and the potential difference would be minus 75 millivolts. But when I have all the ions in the proper mix and I take into account the permeability of the membranes to different ions, it's not the same. I will get overall, I get a negative potential on the inside and a positive potential on the outside. And for mammalian cells, it's roughly minus 90 millivolts. And this is called the resting potential. So resting potential inside with respect to outside is about 90 millivolts, right? And both these ions, potassium and sodium, play the most crucial role in determining these potentials. And this is called the resting potential. If you take a neuron which is unstimulated, not triggered, either chemically, mechanically, or electrically, it's in a state of rest, the neuron will be polarized. One, there's a separation of positive and negative charge. It's in a state of rest. Therefore, this potential difference is called the resting potential. For mammalian cells, mammalian neurons, this resting potential is almost 90 millivolts. And in the next lecture, I'm going to describe how is this neuron excited. When this neuron is excited, these potentials reverse. That's called the action potential. And potentials reverse because of the Nernst equation. ions diffuse across the membrane. So ionic transport across the membrane leads to creation of a potential. Now, this is a strange mechanism of electrical conduction in which charges are moving not, they're going to move parallel, but the charges are moving perpendicular to the direction of nerve conduction. And that triggers the motion in parallel. Nature has come up with this beautiful system of charge transport. Everything is happening at the level of the membrane, ions, Nernst potential, potential energies, concentration gradients. That is at the heart of how we think, how we feel, how we respond to touch, our emotions. Electricity is at the heart of it. All right, so see you in the next class, please.